Okay, so over here in GlowScript, I have set up the two equations of motion for the spring pendulum that we derived in the previous video. Remember, this problem has two degrees of freedom, so it has two Lagrangians equations, meaning it has two equations of motion, one for theta double dot and one for L double dot. I've got the theta double dot up here first. We need to be able to pass any possible information we might need to this function. So this function has a lot of input parameters, actually more than we need, but we might go back and add in, a damping term or something like that. So it's better to just go ahead and put in all of the information that you might need. So here, for example, I've got the length of the spring, the rate of change of the length of the spring, L dot, the theta value, the rate of change of theta, theta dot, gravitational field, the rest length of the spring, and the mass. Now those last three are constants, so I could just declare those as global variables, but again, just to be complete, we'll just pass everything as arguments to the function. Yes, there are issues of efficiency on that. It's not going to come up in this situation. And so here we put in our equation for theta double dot that we had last time. This thing has two negative terms, right? That's the thing that makes it sinusoidal. It makes it restore going back toward equilibrium. We have our term involving conservation of angular momentum. We have our neat L dot over L, that thing I was geeking out over at the end of the last video. And then we have our traditional And then we have our traditional pendulum term, negative G over L sine theta. We didn't talk about this on the last video, but it's worth noting that all of these terms end up having units of 1 over time squared, right? Theta double dot is d squared theta, dt squared. That dt squared does have units. It carries units of 1 over time squared. So here I've got length over time divided by length gives me 1 over time, and then I have another 1 over time, so I get 1 over time squared. Here I get distance over time squared over distance, so I get 1 over time squared. So then we'll return that value here. So that this theta double dot and this L double dot are going to get updated each frame of the animation so that we have the current acceleration for that generalized coordinate. Let's take a look at L double dot. L double dot has this first piece that is related to the theta dot squared. So this guy needs to have units of meters per second squared. So here I've got units of meters. Here I've got units of per second squared. Here I've got units of meters per second squared. So that one's already taken care of. And then here I have this interesting combination of K over M. So your spring stiffness K has units of mass per time squared, or if you prefer, force per distance. So I'm taking force per distance dividing by mass, that gives me an acceleration per distance, or just 1 over time squared. Here I pick up my missing factor of distance, so I will have distance over time squared. It's always worthwhile, even if you're not plugging in numbers, to check the units, the dimensions of your quantities, to make sure everything is matching what needs to go on the left-hand side. So those are the two pieces that are going to drive the behavior of this system. The rest is really just implementing the Euler-Kromer method. So here, for example, we're going to have to set our initial conditions and constant. So this is where you get to play around with where does the spring pendulum start out in terms of where is it located, theta and L, and how fast is it traveling, theta dot and L dot. So these are all the dimensions you need for the initial conditions. And then we need to provide the mass, the spring stiffness, the gravitational field, and L0. And I just realized that I made a big deal about passing these constants here. I did not pass K as an argument, so why don't we put K in here? Again, just for completeness sake. It's not really necessary because it's going to default to assuming that they are global variables, but it's just a little bit cleaner to make these things functions, I feel like. Okay, great. So then what we'll do, we'll create the visual for the pendulum bob. Since this is in GlowScript, I get to actually make an animation out of this thing, which is always cool. So we'll set up our X and Y. So GlowScript is explicitly written in Cartesian coordinates. We don't get to really use polar coordinates to create where things are. So we're going to convert, right? We're going to use this conversion between the polar coordinates on the right-hand side and the Cartesian coordinates on the left-hand side. Here's our pendulum bob. We'll create it using the sphere function. Give it its initial position, and ask it to make a trail. This is where it's going to make a nice, pretty pattern for us. That's just going to leave a trail behind of the trajectory that the pendulum bob follows. And then we'll create the pendulum arm. GlowScript has a helix object to actually create a spiral spring, which I think is great for all the springs that we love doing in introductory physics. This thing is going to be anchored down at the center of the view screen, and then its second end, its axial end. Oh, how do I say this? Its ending point is then going to stretch down to where the pendulum bob is. So we're always going to have its axis equal to bob dot position. And then it's time to animate. The way we create this animation is with something called the Euler-Kromer method, where we just pick a small number for the time step. So we keep on having these 1 over dt's, 1 over dt squared, etc. This is the piece where we actually implement the calculus, is by picking a small number that represents a very small step forward in time. How small is small enough? Well, you keep decreasing it until you don't see a difference in the animation. Eventually, you get down to where your dt is so small, you're not getting any more benefit from the accuracy. But you are increasing how computationally intensive it is because you're telling the computer to make more and more computations for your animation. So you find a happy middle ground of the DT that you want to use that gives you the accuracy you want, but gets you out in time for dinner. We'll start our initial time at 0, and we're going to run this thing for 100 seconds. So the while here just means we're going to run the next block of code until time reaches 100. If you want the code to run longer, change that 100 to 200 or 1,000 or 1,000,000, however long you want to make it. This next line sets the animation rate. Don't worry about it, just leave it. And so what we're going to do, we're going to calculate the 2-second derivative. So the Euler-Kromer method starts with the second derivative, uses that to update the value of the first derivative, and then uses that to update the value of the function itself. So we start out with theta double dot and L double dot. So we're just going to calculate those two values. We're going to call each function once, store it in these temporary names TDD and LDD. Then we're going to update the first derivatives. This is literally just rearranging the equation for the derivative, right? Derivatives equals delta quantity over delta time. So we just rearrange that to get delta quantity equals derivative times delta time. That's exactly what we have here. We have a derivative times delta time, a derivative times delta time. That creates for you how much the function changes by. So my theta dot is going to change by this combination. My L dot is going to change by this combination. That's literally all you're doing in those lines. You're adding a tiny piece to the value you already had before to update it. Then we do the same thing down here with theta and L. So we went from second derivative to first derivative. Now we're going from first derivative to original function. This is integration, but it's integration in a way that the computer can handle it one step at a time. So again, take the derivative, multiply by time step, take the derivative, multiply by time step. That's what each of these quantities changes by for that frame. And we keep repeating this process. That's the purpose of the loop, is that in each animation frame, you are updating the value of theta and L just a little piece at a time according to the physics that we solved for with Lagrange's equation. Now, that will take care of the math, and GlowScript will just internally know that that's what's happening, but we have to actually make it show up on the screen, right? So here's where we update the graphics. We're going to update our values of X and Y, and then we're going to update the bob's position value. So we take this new X and Y, and we say, okay, the pendulum bob should now be located at my new value of X and Y. And that also means that the pendulum arm, the axis, needs to now move to bob dot position. So we're going to update the ball's location. We're going to update the spring's orientation. And we'll update time just so we know when to finish the thing. When we are finished, we will get a print message. You notice that all of these lines here are indented. Indentation is your way of telling Python that this chunk of code needs to go underneath this while condition. And everything that's not indented, we're going to wait until we finish the loop. So all this indented stuff is going to get repeated 100 divided by 0.01, so 100,000 times. 100,000, 10,000, 100 divided by 0.01, 100 divided by 0.01, 10,000, excuse me. It's going to get repeated 10,000 times to create the animation. Okay, let's run this program and see what we get. So here's my pendulum on a spring. You notice it's still got the same general motion as a pendulum. It's swinging back and forth, but we're now combining that with the motion of a spring in and out. And we get this really cool trajectory here. where it's kind of making this U shape, right? That kind of gives you a picture of conservation of energy. But I also want to note this is really similar to what we had in the tracker video, right? So in the tracker video, we saw it doing this. We saw the trajectory take a shape kind of like this, where it never quite repeats itself. It keeps kind of exploring inside that that window that it's not quite a U. It's like a fancy U-shaped window that it's kind of trying to explore. It can't go any farther up than this. It can't go any farther down than this. It can't go into this corner. It can't go into this corner. It's kind of following this track, and it's allowed to wiggle inside the track there. And now the fun thing we can do is play around with the initial conditions. So if, let's say, for example, I want this thing to start stretched out a little bit farther. And so instead of starting it stretched out at 1.3, I stretch it out to maybe 1.5. We'll let that save itself, and we will run this. So I started out a little bit farther out, which means it has more energy to start with, right? I start out with a little bit more potential energy, so it's able to move faster and it's able to move farther. And you see I get a different shape here. It's not quite that same little U shape. Now those corners have become a little bit rounded out because it's able to go out farther, right? I'm expanding the space that it's allowed to inhabit because of the additional energy that I put into the system at the beginning. And now this spring pendulum looks a little bit cramped. Why don't we make it start out a little bit farther out? I'm going to change L0. Let's multiply this by a factor of, say, 5. And let's do the same thing here. Let's stretch L out by a factor of 5. So it's still the same ratio between the two. But now, let's keep this in the same window. But now I will get this... oh, no, wait, that is going to scale to be the same thing. Excuse me. Yeah. Let's make this L 5.5. There, that's what I was thinking of. And you notice now it hasn't stretched out as far, relatively speaking, right? Because it starts out very close to its equilibrium length. So in terms of the spring, it's very close to equilibrium. In terms of the theta, it's not very close to equilibrium. But you notice I get motion that's much closer to the original pendulum, right? It's tending to more swing this way than it is to swing this way because I'm not giving it a very strong L double dot. I'm giving it a pretty good theta double dot, but my L double dot's kind of limited by how far it can move around the equilibrium point there, which is kind of cool. So I'm not getting that flare out at the edge at all there. It's much closer to more of a traditional U shape there. Now, of course, I can also change the theta setting. So why don't we have this thing start out a little bit farther out. Let's see. So if I go to 90 degrees, that's pi over 2, so about 1.5. Let's go just shy of 1.5. Let's try 1.3 in terms of the theta. Now remember, this theta and this L, they control very different things. So like right now I'm starting farther, I'm swung farther out to the right. I'm still starting with the same initial spring stretch. And you notice I get very similar results here. It's wiggling within this very narrow U. So you can kind of think of it like your initial theta controls how far this way it can swing, and your initial L is controlling how far within that U it can oscillate in and out. Maybe we try the other extreme. Why don't we try an extreme where we give it a very small initial theta, say 1/4 of a radian, and let's give it a significant initial stretch. So let's see, if its L0 is 5, why don't we start it as high as 3? So it's going to start out scrunched. And you notice now it's tending to emphasize the pendulum side of the motion and you notice now it's starting to emphasize the spring component of the motion rather than the pendulum part of the motion. It can't get this way very much, but it can stretch in and out a lot. And again, so they're all working off of the same pool of energy, but I've also got to worry about conservation of angular momentum. I've got to worry about the direction that this force exerts versus the direction that the weight exerts. And all of that is taken care of in the Lagrangian. So Lagrangian is this wonderful construction that takes care of all of that. Everything we care about in physics is encoded there in the Lagrangian and gives you these cool results like this. Okay, so the thing I would like to try next is to recreate our tracker experiment here in GlowScript. Now, I put myself unintentionally at a little bit of a disadvantage because I did not write down the mass and the spring stiffness. I know my local gravitational acceleration. So let's try to get the initial conditions off of this thing. So let's start with the position angle. Okay, great. And versus time. I really just need a starting combination for these. I guess the thing I would want would be to get the information off of here. Oh, okay. I tell you what, actually, why don't we do it this way then? Let me grab my x and y off of here. So my initial x, pretty darn close to 0. So what I'm going to do is, let's put another line here. Trying to recreate tracker, exclamation mark. So let's say x equals 0, y equals negative 0.390, and then we'll have L and theta come off of there. So my L would be equal to square root x squared plus y squared. Of course, my x is 0. I might as well just put it as y there. And my theta is going to be arctan of y comma x. Right? Hold on. No, wait. You define the angle this way. This is actually the other way, isn't it? Okay, yeah, my theta is actually equal 0. We're just going to call theta equal 0. Fine. Oh, I could have just done that up here, Brian. Okay, let's try it this way then. If it's that simple, negative 0.390, excuse me. 0.390. Okay, cool. Yeah. So that ought to give me my theta and my L there. My L dot, can we get, let's see, if I go to the velocity, I get the velocity x component and the velocity y component. Or what I could do would be to get the velocity magnitude, right? My initial velocity magnitude. Let's zoom in on this guy here. Nope, there's the zoom. Okay, my very first velocity value is 0.6. Okay, so my velocity, my initial speed is 0.6. So my initial speed is 0.6. So what I can do with that, how do I want to do that? Oh, you know what? I don't need to do that. Because what I can do, I can get Vx and Vy off of this thing because it starts out so close to being vertical, right? Because it starts off so close to vertical. My y component is actually my L dot, and my x component is actually my theta dot. So this is going to be a negative 0.4. Let's go with negative 0.4. Now the thing is, this up here is the linear velocity. I want the angular velocity, so I need to divide by L, 0.390, because you go between linear velocity and angular velocity by dividing by the radius, and that's my radius there. Then my L dot is going to be my y velocity here. I've got a starting velocity. It's stretching. Let's see, it's going up at the beginning, so that's going to be a 0.45. So that's actually going to be a negative 0.45 because this going downward is the direction of increasing L dot. So if my velocity is going up, then my spring must be getting shorter. Okay, the mass of that thing, I'm going to guess, is about 50 grams. 50 grams? 50 grams would be this much. No, that was more like 100 grams. Let's make it... I think it was about 100 grams. This spring stiffness, these springs, these demo springs tend to be about 10 newtons per meter, so we'll use that one. We use our gravitational acceleration 9.8. This thing did not have a rest length of 5 meters. It had a rest length of probably half a meter. I don't know. So just with those estimates, let's see what we can get for this thing's trajectory. So we'll go run. And now on GlowScript, I will be seeing the trajectory. So up here, I need to recreate the trajectory. So let's go with my y position versus my x position. Oh, bother. Auto scale. Hey, there we go. Oh, dear. I need to change my time step. So you remember I talked about you just change the time step so you get what you want? Well, we apparently need to decrease this time step even further. Let's try 1e negative 4. Run the program, and the animation rate will automatically adjust for that, so it will still show me the animation in a reasonable amount of time. What happens when it jumps off like that is it came very close to like the center or something like that, to where it just had to divide by 0 somewhere or something, and that's really only going to happen if the time step is too small. Okay, so let's see. So for my trajectory, I had this whole pretzel shape here. I get something a bit similar. I'm not sure what's going on with the fact that this comes up a lot farther than this one does, right? Because this one is, the tracker is shaped much more in like a box, whereas this one is shaped more like a wedge. So that suggests to me I probably need a little bit more energy in the system. I'm happy with my initial position and velocity. I tell you what else I can do, just to get an idea of this thing. I could make a box to show the position of this thing, like the 4 corners of this box. So why don't we put a sphere in each of those corners? So what I'm going to do, I'm going to make a sphere with a position equal to this upper left corner. That's about negative 0. What is that up there? It's at about... where are you? Do I have a trace on this? That's at about negative 0.33. Excuse me, in the y. My x, it needs to be negative 0.1. 0. And then radius equals 0.1. We'll just make it a small sphere. What I'm going to do, I'm going to put a sphere at each one of these corners. Corner here, corner here, corner here, corner here. And then I have an idea of what to play around with to try to recreate this trajectory. So let's see. So my lower left is going to be at about negative 0.52. And now I can just copy and paste these two and get me the upper right is going to be at 0.11. Nice and symmetric, about 0 there. I like that. And then my other one is going to be at... I need to adjust this one to get me the... That is going to be the upper... Yes. Yeah, okay. Yeah, I just have to change this one's X value. Okay, so now when I run this, I have the corners of a little box there. Oh, that radius was much, much too big, Brian. Okay, so we'll decrease that by about a factor of 10. Okay, do I have these set up correctly? I'm going from... negative 0.1 to 0.11, negative 0.33 to negative 0.52. And so this gives me an idea that I am way exceeding this box, right? So the white corners represent the box that this thing was in. So I have this thing going way too much. I actually need less energy. I'm glad I checked that quantitatively. Let me just... double check this here. Oh, you know what? This is probably too big, because this would... Let's decrease this to maybe 30 centimeters instead. That's probably the biggest unknown that I have. Okay, that got me a lot closer. I'm getting a lot closer to inside of the box there. I could actually use a little bit more energy, so why don't we split the difference and make this a 0.4. We'll click Run this program. Okay, yeah, I just need to keep splitting the difference there. So let's see, so 0.35 maybe? Okay, yeah, I'm decently happy with that. That's getting me to the left, to the lower corners. Now, what about the upper corners? What do I need to do differently to get to those? I mean, you see it's got the same kind of general pattern going down here. It's just it's not getting up to here. I wonder if it needs... Do I need a little bit less mass? Maybe I was right and this is a 50, not 100? I could go over to the storage room and look and find out. Okay, that actually works. That works notably better. You might notice here, let me pan here. You might notice here that I'm now getting to those upper corners. This is a lot closer to this now. Okay, let's go back to a 0.4 on this. Okay, yeah, this is getting a lot closer. Oh, that's interesting. Y'all notice how it's doing that, kind of like an S kind of thing? I wonder, is it ever going to turn around and go down on this side, or have I stumbled on some weird resonance pattern for this thing? Huh, that's interesting. Definitely different than what I have up here. And what I hope this will show you is that, yes, this thing is very sensitive to the initial conditions. Okay, it is filling over that way. Okay, that's good. That's good. Okay, yeah, there's probably a little bit more to tweak with that, but I'm actually pretty happy with this. It's really neat to be able to get the simulation to match so well with the experiment that we did. So what we'll do next time is take a look a little bit better detail at the simulation. We'll move it over to Jupyter Notebook and get a better look at a lot of the quantities that we're interested in this problem.